Hi everyone, today we're going to talk about PlanarSLAM, RGB-D SLAM with structural regularities for indoor and outdoor environments. VSLAM needs to deal with multiple types of dynamic environments. Indoor environments, among all the scenarios, is one of the most difficult to deal with due to a lack of textured surfaces and irregularly distributed feature points. One common issue for VSLAMs to deal with indoor scenes is the small errors accumulating over time, as the map is built from a sequence of input frames. Consequently, drift occurs and it may affect dense reconstruction by resulting in misaligned surfaces and artifacts. In our project, we ask the following question: can we carry out a low drift SLAM to improve the post-estimation and the reconstruction accuracy of very challenging indoor scenes? Our solution is PlanarSLAM. Furthermore, we ask if this low drift SLAM can also perform well with outdoor scenes. We will compare its performance with ORB SLAM 2 in both indoor and outdoor scenes. This figure shows an overview of the PlanarSLAM framework. Indoor scenes are modeled as Manhattan world, where statistical image regularities arise from the geometrical structure of the scene being viewed. Point, line, and plane features are extracted from the RGB-D frame. Rotation and translation are estimated in a decoupled fashion first and refined afterwards, reducing the drift generated from frame-to-frame tracking. The planar segments are used to create a mesh-based reconstruction of the environment.
We manually adapted the PlanarSLAM to three kinds of datasets with different difficulty and scene. The hospital dataset is the indoor dataset from Titan Air and is the ideal scene for the PlanarSLAM. And the abandoned factory is the outdoor dataset, which is hard for PlanarSLAM. The tunnel dataset is another one we use to test the performance of the PlanarSLAM with cylindrical scene. The indoor situation is the most ideal one for the PlanarSLAM, since the plan features would be well recognized and the pose could be refined by the Manhattan relationships. As we can see, the plans like the floors and the walls could be well recognized and marked out. For the abandoned factory, we can see that the points and lines have been figured out. However, very few plans can be recognized due to the far distance and the discrepancy of the Manhattan world assumption. The cylindrical tunnel is another challenging situation. The walls are not a planar surface, so that it could not provide two perpendicular elements for every frame.
This figure shows RGB in RGB-D mode. Due to the color diversity of RGB image is considerably low, the performance is unsatisfied. Next is RGB in monocular mode. It can deal with the misclassification problem to some content, but its shortcoming is obvious as well. The built map point cloud is sparse and is very sensitive to dynamic objects, so it's quite easy to lose track. As for our proposed PlanarSLAM, it's easy to find out that the algorithm extractor achieves an excellent performance on points, lines, as well as planes. And the following two figures show the relative pose error between camera trajectory, keyframe trajectory, and ground truth. Basically, the RPE is around 0.8%. In addition, compared with RGB-SLAM, the tracking time of PlanarSLAM is larger because it extracts features from higher dimensional levels, while the cost is to sacrifice more time.
In conclusion, our RGB-D SLAM system achieved the state-of-the-art performance with acceptable relative pose error. However, it resulted in some limitation of the system. Like we mentioned before, it's hard to estimate the pose in the outdoor environment. Once it lost track, it can hardly relocalize. It also has a problem detecting the continuous cylindrical surface as a plane. So in the future, we will implement the cylinder extraction and mapping algorithm from FastCape in the RGB-D SLAM system to improve the accuracy and the robustness of the process. Thank you for listening. Any questions?